Welcome everyone. So this is chapter 8, the part 2. Last week, briefly, we mentioned what were the packages used in the book for making analysis. And we saw a case study on how to use MLR3. This week, we see how to use KIRAS on a general infection dataset, a synthetic dataset. And so just briefly, what we did, we saw that some meta packages, the engines, and then specialized packages for various type of analysis. So we just mentioned this, what were the most useful packages at the moment available for machine learning. And then, as I said, we have seen briefly how to use MLR3, which is a quite intriguing meta package. So it requires you to spend a bit of time looking through the documentation, but then it's quite interesting, we saw, because you can visually see that you can set a task, specify a model, and then so work through it. What we do today is get into neural network. Okay, deep learning neural network. And so TensorFlow and its interface, it's our interface, which is KIRAS-3. Okay, KIRAS-3, what is KIRAS-3? KIRAS-3 is a high-level neural network, API, application program interface. And it is not the R interface, but the original Keras is written in Python and capable of running on top of TensorFlow, CNTK, Theano, and so on. So it allows for easy and fast prototyping, supports both convolutional networks and recurrent networks, and run on both CPU and GPU. Okay, so now let's say that we don't know anything about those things. How do we do to get started? So this is, I already lost it. Okay, this is KIRAS-3. I put in the chat documentation. Okay, just for you to get started with it. What you need to do is install packages KIRAS-3, and then once you have installed it, you need to set up a backend engine, and our engine is TensorFlow, as we mentioned. Now we explain a bit more, and to do that, you call it the package KIRAS-3, and then install Keras backend TensorFlow. Once you have done those things, you should be good to go. And I don't know if you have any question. If you tried installing KIRAS-3, if you had any issues, or if you just have any other general question on this bit. Okay, so just to introduce a bit, TensorFlow is as I said, backend. It's an engine, okay, built on Python language. And what does is performing neural networks. That means that it's a high level of modeling and very to cut short and to go straight to the point, is like something like, it makes a basic model, check for the level of error, adjust for a new model, and then repeat this process until it's happy with that. Okay, this is very, just simple, basic explanation, just for you to visualize what is happening in it. So it's like a high level calculator, okay, such as you don't need to know how to manually calculate a logarithm, for example, because the calculator does that. And this is what's happened within this type of things, that we cannot visually immediately realize what's happening inside, but we with a bit of background knowledge of the mathematics and things, we then apply those things to the model, which is our sort of highest level of calculator, and obtain an answer. Okay, so the book, this is okay, that was the second example. So here, this is the second part of the chapter, and here what I did it is to like simulate some data. Okay, and this is something that we already have seen in a previous chapter, and set up say compartment model, okay, where we have some parameters, so the beta, so the various infection rates, incubation rate, and recovery rate. Okay, I'm not going through it because Chantal did it brilliantly last time, so exactly the same. And why we do this is because we need this function, this model function, and what we do is basically applying neural network to be able to update, in some senses, update very in a very simple and basic way, just to make understand, just to be able to understand the process, what's happening, to what's happened within it. So what we do is basically updating the parameters with neural network, and then apply this update to our say model function. Okay, so this is what we saw already. We have the model function and a certain output, okay, which is a data frame. Let's jump into R to have a quick look at just close that. Okay, so okay, let's have this just we run this bit. Okay, and we need the solve package to run the function, which is the odd function that is able to calculate the differential equations. We already saw that. So this is our data set. Okay, we already saw this, and we are interested in this vector, so the infections. Okay, and what is important, just realized that I haven't. So basically running this bit from the book. Okay, we can see that the output is this one here. And as you can see, what we are interested in is in this vector, and this vector is the infection vector. And what we do is basically to consider for predicting infections, we need to consider other parameters, such as, for example, social interactions, because social interactions are very important for correctly identify the growing number of infections. And this is, in general, can be everything distance, or particular location, or some other characteristics that are able to, people to interact with each other, that allow people to interact with each other. And to simplify, what I did it is to basically simulate these social interactions with a simple resample function and a random normal function. And we can see this here. Okay, so what I did it is consider 1,000 number of samples, which is our individuals, okay, and 10 features. These 10 features are, as I said, the distances, they are standardized values, okay, as you can see, because I simulated with our norm function to be normally distributed. And so they comes like, even if like they are standardized, okay? And you can imagine this X1, X2, X10 to be like distances to specific amenities, and so various factors that influence the growing of infections, right? Okay. To these 10 features, I add an infection vector, which is just a vector of 0 and 1s. So just to identify, 0 not infected, 1 infected. Okay, so this is our social data that we use to basically update our parameters, such as the infection rate in particular. Okay, because, in our simple basic model, we established that we had an infection rate of 0.3, but that is not enough. We need more parameters, because in reality, more parameters influences this infection. And so we use a social, some social features and build a new data set. So we have a new social data. Then we leave the Zaire model, and so all the starting point on a side for a minute. And we use just this social data and apply neural network to social data to be able to extract an average value of infection after I predicted this value, and use that to update our model, original model parameters. Okay, so how do we do to apply neural network to this social data? Install the package Keras 3, install Keras backend TensorFlow. You should be able to be able to, so it should work, should be able to work on it. And the function that we'll be using are this function here, Keras model sequential, which is model function such as a recipe thing. And then we add a layer dense, which is a feature to the base model function. And then a layer activation, which is a further level of the this type of modeling, okay, of this neural network techniques. And then we finally, once we have these first three functions allowed you to set a model, okay, you in this way you have your model specified. Then what you do, you need to compile the model, and this basically what does is checking if the model is doing fine, applying a loss function, and so basically checking the error of the function of the model output. And then when the calculator is happy and release an output, you can finally fit the model. Okay, this scenario is this one here. So we have a data set with a number of cases of a general infection and various features. We build a neural network to update our Zaire parameters model based on certain social feature interactions. And so basically what we are going to do is this. We are going to update our beta with the mean of our predicted infections out of that they came out of our Keras model. And then apply this new model to predict the number of infections based on social interaction features. And to be actually compare these two, the original basic model to the new one, and see what changes. So a neural network model starts, okay, these are our features. As in general, a model is like y equal to like beta 0 plus dx, which are the features, the xy. So we can we don't use I for general, and then a beta 1. Okay, so this is a basic, very starting point of a model. And this one here, which is the first layer, is exactly the same. Okay, so this bias here, it's like having here put an error term. So the error term is here is the bias. Okay, we are focusing on this bit, which are the weights or the betas, and the X are the features. Okay, so this is basically our starting point. We are starting with a basic model, just changing the name of the variables, just for you to visualize this thing, and then run this model. Okay, then what's happened is that we have an output. Okay, so we have obtained a new matrix. Here I have our Y, that in this case are the Z. One. Okay, and here we have all our output, our Z. And this is what we obtain with this function. Then this is just the first level. Okay, this is just regular modeling. Okay, what neural network does is going deep with it. So searching for a way to further apply a selection of these elements. Okay, in this case, we apply an activation function, which is a ReLU. A ReLU function is just like a function that says it's always 0 and sometimes 1. Okay, this is so start from a basic 0, and then maybe that this is not so we apply this function to our new vector, to our Z, and select all the elements that are greater than 0, just to make it short. Okay, 0 or greater than 0. All the others, we don't need them because we don't want. You can like select different type of activation functions. There are different type of functions that are usually used. There are sigmoids or you know, other function that they depends on your decision on choosing one upon the other. It belongs to the fact that you need to know the phenomenon that you are analyzing, and thinking about what so for example, in our case, we don't need negative values, just to give you an idea. So our model will be filtering out this value and keeping just those ones. So what's happened is then after that, it might seem like strange, but it is, as I said, just a calculator. We know the background maths, what's happened behind, but sometimes it's difficult to you know, visualize what is happening. So we apply a sort of filter that we called activation function, and this is our first one. You can have as many as you like, you know. And then start with the second layer. Okay, what is this second layer? So we now have a new data set. Okay, and we just rerun the model to our new data set, which is filtered because it's passed through this activation function. Yeah. Okay. So second layer, same thing, all the same. Then we might decide that two layers are enough. And so we finally apply our output activation, and this time we use a sigmoid. A sigmoid is this type of function. So the output of the second layer will be positioned inside this function, and it will throw out a second output. Okay, we might be happy with that. We might not be happy with that. We can go further on applying a third layer, or we might start doing dropouts. Okay, because there is even the opportunity to go back and drop out other things and many things. So obviously this is just an introduction. If you're interested in it, you need to look at a bit more in depth. So let's start applying this function. The main function is this, Kira's model sequential. And then we have some parameters that we add. In this case, we apply this input shape, and then so just to go back. Here. Social features, these are the okay. So usually what you do is taking the function like question mark and enter, and you have now I don't have the model loaded. Then you have the explanation of what's happening and what is this function. Okay, so this is a model. Okay, and you have some argument that you can specify. The input shape is a shape integer vector, and in this case we decide to apply this type of specification because it's easier and simple. And then you'd see what's happening with the output. And then once the model is specified, we start with the first layer, and then we specify unit 1. To keep it simple, you can play with it. I don't suggest you to do that too much, because the differences sometimes are very tiny, very little, and then so keep it simple when you get started, and then apply the first activation ReLU. So I can pipe all of them. Here, in the second layer, I've put them all inside the same function, but I could even split them in two, as in the same in the previous two layers. It's exactly the same You can like avoid using layer activation and put the activation inside the layer dense. So this is our model. Basically, it's, if we go back to R now and we run, because in the notes I haven't put anything of those things, so we just need to run that a bit. And our P in this case is the number of features. And so let me do that first. Okay. So we create the model, and it shouldn't take that much. It's quite fast, and our data set is not that big, because it's like 1,000 observations, so not that big. But anyway, it takes a bit. So then what's happened is that, okay, now it's done. If we look, as you can see, I haven't assigned that to anything, because this is another characteristic of another feature of this Kira style, the type of models, is that like memorize the things that you do, and so you don't need to assign your pipes to a new name, because it's automatically recorded. And here is our, if you want to have a look at the specification of the model that we have just built, is done with, we have 13 parameters, and we use an activation function on the first layer, and then the second layer with the result of some selection. Okay, so this is a type of model sequential, and it is nice to see this. Like we don't see what's inside yet, because what we do now is that we need to compile the model. And this means that the output of this this model will be then compared with a loss function. Okay, we will use in this case a binary cross entropy function, which is usually used for binary output, so 0 and 1, not infected and infected. This is the mathematical formulation, and it's a loss function. So it's like an average that you like do the difference between the original value, the model output, and then calculate a sort of average within these values, and check the accuracy. And so this is all done with a compile function, which is a compile. And then we can specify different type of loss functions. In this case, which, as I said, we use a binary cross entropy, but we can use others. And then we can use an optimizer. Okay, this is even like interesting. Okay, this optimizer, I don't know if I've mentioned something in here. Okay, this is done to match, as I said, the differences between the original data and the model output. And you can have a look at the documentation for more specification about this type of optimizer. And then you decide for a metric. In this case, we decide for an accuracy. So even in this case, you don't need to assign this to a name or to an object, because it's enough that you pipe the model to a compile to the function, and it automatically store the output in the model. So now, if we have a look at the, we run this compiler, we don't see nothing. So, and then, but something is done. Okay, so the model is now compiled. And what we do is now fit the model. Okay, and to fit the model, we use the fit function. And inside the fit function, we need to specify the data as a matrix. Okay. And what is our output? So in this case, the infection. And then here are three factors. So three parameters of the model that we can adjust. Okay, this is our first try. And so we define this as to be history 1. And we can assign this to a name, to an object, because anytime you fit the model, the output changes. So if you want to compare two models, you need to assign this to a name. And this is what we did it. And then you can plot the output to visualize. In this case, we have the epoch, the batch size, and the validation split. Okay, let's start with the validation split. Means that you're just leaving 20% of your data for validating the model, so as a test set. Okay, such as a test set. So you basically run the model, even test it, and then you validate to left 20% of your data to finally visualize, test, see how it works on new data, completely new data. So we are not rerunning on the same data. And then there are this epoch and batch size. And then you need to go through the documentation, because you can vary this. And we did that into, what is the twice. Okay, so we use, this is history 1. And then we did it again with history 2 with a different epoch. So basically what we did is just cut that on a half. Instead of using 30 epoch, we used 15, so the half, and the same thing with the batch size. To cut short, we have a look at the output of these two, because we can see, and this is quite interesting. As you can see, this is history 1, and this is history 2. These two outputs, the first one shows a bit, they should like be this way, so concave and convex, so like this way, so that's the best model. And as you can see, the first one is not doing a very good job. So the accuracy, so the loss is performing fine, which is not performing that fine on the history 2. The accuracy is like a bit of like overfitting a bit. the data. And so you might lose some information on new data, while on history 2, you can see that this is like shaping a bit better than the other. And so history 2 is better than history 1. To conclude, you can like test and try different epochs and batches and see how it changes, but then you can consider that you can do model assessment with using different activation functions, different loss functions and things. And so now we are happy with this model, or at least so we accept this one here. And what we do is basically creating a new, imagine that you have now that model, you put into production, and then what's happened that you have new data. So we create new data and predict with this model. We use the model and then predict on new data. Okay. And then use this. So if else the predicted infection is greater than half, put 1, otherwise, because they are like standardized values, so they are ranging between 0 and 1. So we transform them to be 1 and 0. When it's greater than 0.5, will be set to 1, otherwise 0. And update our parameters with 1 plus the mean of predicted infections. We put that inside our, say here, our other function, and adjust the output. And here we can see the difference. Our starting point, our, say here, model function, and our new scenario, the golden one, the yellow one, which consider a greater number of infection in a shorter term than the other, because due to social interactions. And so I'm not, this is fairly interesting. Obviously, this is just an example. So, but it can be, I think it can be useful for understanding how to start and apply this type of models, which are very useful because they are high-level calculators, and so they can like consider other things that you might have. And so this is one way. Then you can do like Bayesian analysis with Stan or other things. This is another way to update parameters with machine learning. And so if I go back to here, I think it's all I've got. We might have a few minutes. I don't know if you have any questions. Yeah, Robert, please.
So I was just wondering if you could just go over the intuition for what the training models, sorry, the model histories was again. So what's the epochs thing on the x-axis here? So is this just like yeah, well, what's going on, I suppose?
Yeah. this is so if we go to it's what is going on is so Kiras is so this is it's you can imagine, you can think of it like a number of tries or something. You here, for example, you have the list of different things and that you can use. These are you can see that as the number of let me see.
Oh, is it just as simple as like number of model runs?
Yeah, it's
Yeah.
the number of tries that you can specify. But let's have a look at the it's like, you know, when you do random forest, when you specify the number of trees,
Right.
so
Yeah.
the number of connections that you these are type of model parameters that you can adjust, and you can even automate them to adjust them automatically. In this case, Kiras, if you do like Kiras.
So as they're increased, essentially the model has more opportunities to hit higher accuracy,
Yeah.
lower error.
It's is it this
I was just trying to get my head around that, why there would be that, why I suppose why the error would decrease as the number of epochs increased.
no, the number of box decreases. The second. Okay. So in the second one.
But why we get the downward sloping curve, I suppose, like what's the relationship there?
Yeah. The I think this is the best. This is depend even on your data. Sometimes even if you increase the epochs, it does better. Sometimes if you decrease, it does.
Okay. So
So
it's more of a case of trying out different parameters to see what works better.
yeah, it depends. Yeah, of course, but experience tells you what is best for your data.
Okay.
Yeah. What else? What other parameters? And even the batch size. You can imagine that you have this. I don't have any other mathematical formulation that I've shown here. Just these simple ones. I've shown here just the simple ones. And so definitely you can like think about a random forest and the various parameters that you specify inside a random forest, like when you like the number of branches, the number of trees, the number of nodes and things. Those things are exactly the same, and I'm not going too much into details because it's out the scope of the book.
Yeah, I know, fair enough.
Yeah, no, but it's interesting to if you use that type of thing, it will be interesting to be more wide on explanation about those things. It is the same with MLR3 and all the type of models that I use. I'm afraid I've just thrown parameters and things that are simple for showing an output and reasonable for the type of data. But Kira's obviously neural networks is fairly interesting, very, very interesting things. And what they did is a huge job with Kira's 3 POSIT for setting up an interface that is very, so it works very well and you can use it with R. So very good question. And what else? I don't know if you have. I struggled myself a bit to decide which what number to use, which one to use. But to be honest, I found so I've decided to use well-known examples, and so like number of epochs and batches that I usually use for this type of data. And you should stick on some numbers sometimes, even if it's not, but these are synthetic data. It might be good or not good for just for so okay, so we are now 2 o'clock, so top of the hour. The last bit of the chapter is about how to find a package, and this is quite straightforward, so I'll leave that to you. This is a couple of ways to do that, and I found them very useful. So you can just like type a keyword and you find a list of packages, then decide which one to use. Okay. Stop the session.